smart edge devices with analytics. So this is even going further in this vision of collaborative IoT, where we equip edge devices and also IoT field devices with more and more intelligence so that they can collaborate more and more autonomously. This slide here, or this illustration, should explain this a little further, so this vision. Chris already indicated that we, in this collaborative IoT, don't want to specifically engineer anymore the production process by doing a lot of engineering on how the robots, so as IoT things, have to collaborate to produce a certain product, for example, in this case, a drive, but we equip them with knowledge about their own capabilities and with reasoning capacities so that they autonomously can find efficient ways based on a defined specification of what we want to have and how to collaborate. And the benefit of that is really that we can easily, at a later point in time, give them a new goal, so define another what they should produce, and they find autonomously an efficient way of reaching that. Okay, so as you can imagine, this collaborative IoT is still quite some years down the line for us to reach it. And I want to draw now this path with some more details. So I give you further building blocks in my talk that lay on this evolutionary path. So starting with cloud-centric IoT, now smart edge, and then what I call now composable IoT. And composable IoT means that we can, as shown in this example, use different components hosted by different IoT devices, for example, sensing with a camera, producing a video stream, for example, then doing some AI classification, machine learning, doing some situation detection, and then acting upon it, for example, doing a quality control in a production process with the camera. That's a simple example of such a composed IoT application. And we were very much interested in tools that can be used to do this, so to compose IoT applications. And a very prominent and popular tool is Node-RED. So who has heard of Node-RED in the room? So a lot. And who has really worked with it already? Yeah, quite few, but still. So just as an introduction, shortly, it comes from IBM Emerging Technologies. It's open source. Everyone can download it for free. And it consists mainly of a graphical editor. You see it here, where you can program so-called flows. This is your IoT application. And these flows consist of nodes. And these nodes you see here on the left side, this stuff. And you can just drag and drop them into this canvas and then connect them, and this connection is then your flow, your program flow. And it also comes obviously with some runtime environment, yeah. So the flow can be executed by Node-RED, and the beauty of it is actually that you can also plug in new nodes. So you have access to an ecosystem of by now 3,500 such components, and you can plug in new ones. So I wanted to actually show you Node-RED in action with a small example. So what you see now here is a virtual machine where I run Node-RED right now. And you see here, first of all, the website, so where you can download it. And here are these components that I was talking about. So you can just search for something, I don't know, for example, S7, that's a famous Siemens product for industrial automation, and you can here download, so I can click on it and then download a module or this node package with several nodes in it that I can then use to talk to an S7. So now let's go to this Node-RED Graphical Editor. You see it here now in my browser. On the left, as I said, there are these nodes. And I will now build a very quickly an application for you, just for you to get an impression and maybe also a motivation to use it in your challenges. So what I do is I access Twitter, since I don't have any IoT devices attached to my notebook right now, and I will search for some Twitter handle, for example, this guy here. So the real Donald Trump, so that's his famous Twitter account, and with this node, Twitter node, I'm accessing now live the Twitter feed of all tweets globally that are being posted from him, which is a lot, but also about him, which is even more. Yeah, so and that I can now easily dump to the console here on the right. So I just plug in this debug node, I connect them, and I have my application. I deploy it, and you see now here a lot of tweets coming in. As I said, live from Twitter. And to make this more interesting now, I can also access some analytics, AI, if you will, nodes. So for example, a sentiment analysis based on the text of the tweet. I can deviate this data flow from Twitter to the sentiment analysis node. And I could now directly connect that here to the message payload and see something, but I think that's not so meaningful. I have to program a little bit, which is also very easy. So I just put in a function node in here. There I can freely program now JavaScript. So I just double click here and I have to, well, I just put the microphone away. So I have to basically specify what I want to see in the debug dump. If I remember correctly, it was sentiment.score. So what I'm interested in is a number, the sentiment score. So it basically indicates from, I think, -10 to +10, the sentiment of a text that you put in this case, tweets. So I say done here, and then I have to basically define the path to the debug console also. I redeploy simply, and now you see here there are numbers under each tweet. If I stop this now for a second, we can take a look. So here's one example. So real Donald Trump, Fox News, how you know somebody is fake. So I assume this fake is an indication for giving a low sentiment. Yeah. No, that's actually it. So, well, you can take a look on your own, experiment with this, maybe also as part of your challenges. I will show you later some nodes that we implemented, and you could also reuse those if you want to. So let's get back to the actual talk. Well, here on the right you see an example from Siemens, so where this could be useful also as just one example. Yeah, so you see here a flow that gets all the positions from the workers in a manufacturing shop floor, for example. And what we want to do is switch off a robot arm if a worker comes too close to it. So what we do is we operate a little bit with the data and then feed it into a geofence, for example, 3 meters around the robot, and then we emergency stop it with an S7, so this Siemens device, which you would see also as part of the challenges. Or in this case, 3 different robots. One is controlled with OPC UA, an industrial protocol, which we could also easily reuse here by just accessing the ecosystem of Node-RED. Okay, at Siemens, Node-RED indeed plays also a role by now. So it comes from this open source community, but Siemens has picked up on this, and we have now a product called Visual Flow Creator. It's an app, if you will, for our cloud platform called MindSphere. And you can just install that there. And also for the edge devices, which you will see as part of the challenges. The first app developed ever for these edge devices is actually an adaptation of Node-RED. And we also have projects in Siemens. This is one example, a manufacturing execution system based on Node-RED. There the flows don't look this small and tiny as you've seen, but they are huge flows of data controlling all kinds of things in the manufacturing shop floor. Okay, so that's the idea of composing applications with IoT. Once you have that, and especially when you base it on an open ecosystem like Node-RED, what you need is, or what you need to establish is trust. And this is also one building block here on our evolution, trusted IoT. Yeah, because with Node-RED particularly, you have a heterogeneous ecosystem, contributions from professional companies, IBM, for example, is contributing, but also hobby programmers uploading something, and we might end up in a customer project using some component like that, and there might be severe security or quality issues related to this. So that's a big challenge for us, and we address this in a project which I will give you a brief overview about. So what we did is essentially crawling the ecosystem and extracting all the metadata that we could find in this ecosystem as it is populated on the web. So we would first go to that website that I showed you also and download metadata there. Then we would follow links on that website, for example, to NPM or GitHub to get more metadata, and then we fill these metadata into a knowledge graph. And that knowledge graph can then be used to do data analytics, for example, regarding quality or security or just license clearing. And that would then for us at Siemens be usable, for example, in a portal where we offer approved nodes to our customers. This is a semantic data model. Maybe also as part of your challenges, you might want to develop such a data model. It's simply consisting of triples, so subject, verb, object, and can be then stored in a knowledge graph. Here, for us, the node package is a central concept with several properties attached to it. Then we do a code analysis, so we download the source code from GitHub and run an automated code analysis. We have information about the repository and about the flows that are also stored in the ecosystem. So as I mentioned earlier, we do this, we crawl the ecosystem for all the 3,500 components that you find in this Node-RED ecosystem on the website, and then we basically rely on the structure of the HTML page. So what we do is we download all the textual data that you find and put that in the knowledge graph. We structure it a little bit and then it's machine interpretable. Here's the static code analysis. So we use ESLint for that, download the code and then run this analysis and store the information also. Overall, this process takes around 6 hours to crawl the entire ecosystem, and then we produce around 650,000 triples for one ecosystem crawl. Obviously, you have to do that multiple times or keep doing it to keep it updated. Now regarding quality, so we could now look into different properties that we find in this knowledge graph. For example, for quality indicator, what could be interested is the last update or the community rating, the results of the code analysis or the number of open GitHub issues. And all these things can be found in the knowledge graph and could feed into a quality index. So that's an example for a project that tries to establish more trust in IoT ecosystems. Once we have trust, we can really think about also this aspect of decentralization. I mean, there was also a question that came up after Chris's talk. And I want to talk a little bit about this here also. if you think about these IoT compositions, applications that consist of multiple tasks or components, for example, in an AI pipeline. At some point, you will have the need to actually distribute that on multiple devices. And since we are developing right now this smart edge environment, we actually have more and more devices, edge devices available in the industrial setting. We could use that to distribute the entire application and have a decentralized application running on the edge. Yeah. And once we can do that, actually we thought about how to optimally do that. So optimization could have different goals. So for example, making it most responsive, so increase or maximize the performance of the overall application run. We can also think about making it most reliable. Yeah, if we have indicators about the reliability of each of these devices, we can deploy crucial tasks on these very reliable devices. Or we can think about energy consumption, yeah? Especially in constrained environments with wireless devices, this is relevant. So we developed a solution for this that takes a network model and an application model as an input, and developed an algorithm based on integer linear programming that finds this optimal solution. And we evaluated this also in a small scale setting with 6 devices, and we optimized towards energy consumption because we were interested in this wireless constrained environment. And we found that our solution was actually saving or being more energy efficient, 15% more energy efficient than the average of all the other possibilities. If we look at Node-RED, such decentralization is also interesting. So usually Node-RED actually runs in a centralized way. You see here an example of a flow that streams a video. So this is a node that accesses an IP camera which is connected to my laptop. It encodes that video and displays it all on the same machine. The network connectivity, so the connection to the camera, is actually just hidden here in the configuration of that video access node. So you see here the URL that I specify. That's fine for certain cases, but for us, looking at these edge computing scenarios, we wanted to actually be able to specify where these different nodes are running. So in our setting, in our example, we wanted to have these first 3 nodes running on this edge device and this last one on an HMI device on the edge. And in addition, we want to also make this network connection, so the connection between these 2 devices, more explicit, and for example, specify quality of service constraints on these network links. So we worked on this example and on a small demonstration, which you see here, the setup. So we have at the top the semantic nanobox, which you will also see as part of the challenges. There, the main Node-RED instance is running, where I define the overall flow. There's also the network controller, and via MQTT, this flow, once defined, is then communicated to the dependent Node-RED instances running each on a Raspberry Pi. So one Raspberry Pi has a camera attached, and another Raspberry Pi has the display attached. And the flow is communicated here, and also the actual software nodes are sent to these devices and can now be executed there. And the transmission of the actual data, so the video stream, is directly communicated, so not via an MQTT broker over the nanobox, but in a decentralized way from Pi B to Pi A. Right, so this is how it looks like in Node-RED. I can basically now add further information to this flow of the video stream by selecting nodes and then specifying here via the node requirements on which device it should run. These two here, I'm not sure if you can see that, are running on Pi B, and this one here is running on Pi A. So this is a video that shows that quickly. So you see the setup, the nano box here, and here's the Raspberry Pi behind the camera, and another one here, and this is the network switch. And these screens that you see here are actually showing what's running on the Raspberry Pi. So this is the one on the left, and this one here is this Raspberry Pi. And it was basically initiated by the Node-RED that's running on the nano box here, the central one. I define this flow, the same flow that you see here in the background, and it's directly communicated to these devices. So after hitting the deploy button on the central Node-RED instance, you can see now that, okay, so the audio we don't need. So we see here basically what's running on Raspberry Pi B and Raspberry Pi A. Same flow, different nodes running. And there's a camera feed which is not yet on. And basically what's happening now is we hit the start button there on the left, and the video is streaming on the right. So what this is supposed to show you is essentially that we have now a distributed system between two Raspberry Pis as two edge devices, and we can control the overall application flow via one Node-RED instance and distribute the logic to different components. We can also now specify here the network constraints. For example, a maximum bandwidth can be defined here. For example, if you have in the network multiple such traffic flows, you want to specify for each traffic flow how much network bandwidth it should consume. And also there I have a video which is very short, just to show you or give you the idea of what's happening. I double click on this node which represents the network connection. I type in the maximum available bandwidth for this flow, which is here I think 4.5 Mbit. And we see in the end that the video is lagging a little bit. So that's happening now here. The video is again transferred, but when I move the hand, it's lagging a little bit. So I actually wanted to show this also live here. I have all the Raspberry Pis and so on with me, but I was thinking maybe I show that tomorrow in a coffee break if you're interested. Okay, so relevance to this summer school could be, for example, to implement an AI pipeline with this form of decentralized Node-RED. Here's an example. We are actually already working on this. So you see again here these components that start the video stream, access the video from the camera. They are all running on Raspberry Pi B. Here is a node that represents the network link to the nanobox. And then we have nodes now here for TensorFlow, conversion from an image to a tensor that could run actually on its own device. Another node that classifies the image now, they both run on the same device, but could be also on different devices. And in the end, we could trigger, for example, an S7 to stop the process or something, or act upon what we detect in the image. Yeah. And we are also working on retraining this. So we are using MobileNet behind the scenes here with TensorFlow. We are working on retraining the model to new classes. So if you are interested in this, to use it in one of your challenges, please let me know and I can give you access to the code. Okay, the last building block, I think, in this path that I wanted to sketch out here to you towards collaborative IoT is dependable IoT. So dependability plays a huge role. What is dependability? Well, here's a definition. It's a quality of a delivered service so that reliance can be justifiably placed on the system. Yeah, so it has to do with reliability, obviously. And one aspect in dependability is failure detection. And failure detection in such decentralized environments is really crucial. So we worked on a small student project on a failure detector for especially for constrained devices. Here you see an illustration of this. So you see 4 edge devices and an application that consists of this yellow, green, and red components. And these arrows here are the application flow between these components. And each of these components are running in an engine that we developed that also has a failure detector running. And that failure detector basically observes another device with a heartbeat. And that is basically mutually done. And we have or maintain some sort of suspicion function in the background that indicates if there are no heartbeats coming in anymore, that a failure is likely. So once a failure is detected or suspected of a device, then this is notified to a so-called mitigator, and that mitigator has access to a knowledge base of all the available devices, and we could then figure out where this green component on the failed device can be redeployed to, and then apply this mitigation by simply moving this here. So we worked on this as part of a master thesis and figured out in an evaluation that our work is also quite performance. So we compared against the phi accrual failure detector, which is very well known, used in the ACA framework, for example, and we were able to be more or less equal in terms of mistake rate, a little better, but more importantly, we are using constant resources in terms of memory, which is not the case for the other one, and which is important for us in constrained devices. Okay, that's one aspect of dependability. Another one is reliable connectivity. Also, that's something we are working on. For example, in this use case here, as part of our Semiotics EU project. Here it's about oil leakage detection. You see here a lot of oil leaking out of a wind turbine. We also have this wind turbine case as an example. And we are doing that with a video camera that sends the camera feed to another device to be classified, and then in the end might trigger a PLC, so an S7, Siemens S7, for example, to stop the wind turbine if there's oil coming out. And as an application developer, you want to be able now also to specify quality of service constraints in such decentralized applications to really give you also dependability. So for example, what we want to specify here is a minimum video frame rate that might be required by the classification of the imagery. So in Node-RED, this would look like this. So we again have these associations to devices. Raspberry Pi 1 runs the camera access, Nanobox runs the oil leakage classifier, and so forth. And exactly on this link here between these two, we want to, for example, specify a minimum video frame rate. And what we need now, or what we addressed in a research project, is an automatic translation from these high-level quality of service constraints from an application point of view that are relevant for an IoT developer into very specific network constraints. Yeah, and we did that again with semantic web technology. So we built 2 models, one for the IoT application flow that you see on the left, and one for the network configuration. And here you can specify the high-level QoS constraints, and here you have the low-level network QoS constraints. And in the example of video frame rate, We can now calculate, so that knowledge is basically part of our model also, how to do this. Video frame rate times the resolution of the video times the efficiency of the codec would result in bandwidth as a network constraint, and that would be automatically translated and could, for example, be an input to a SDN controller, so a network, programmable network controller. Okay, that's basically it from my side. I hope this was interesting for you to see what we are doing at Siemens, often in collaboration with universities, and I would be very happy to also discuss these things with you, maybe also to establish some new collaborations with you. We are always looking for also university partners. So, one last thing, together with Dan and another colleague, we are actually currently running a special issue on semantics for sensors, networks, and things in a journal called Sensors with a high impact factor, and you still have 1 month to prepare something for this call. We might also be able to give you a deadline extension if you are interested in this. That's it from my side. You can also. Yeah.
Do you have any questions?
Curiosity from the deployment plan, the optimal deployment plan that you worked on Node, right? Just a curiosity. When you set up the QoS, so the quality of service, you just can set one, or there are ways, or are you studying ways of setting multiple quality of service constraints?
We could require another microphone actually, but is there a way to also switch that on? So for your question, it's actually a very short answer. Right now it's a prototypical state that this is in, so we can only specify one right now. Yeah, I think so, yeah. So we are doing this actually also as part of the semiotics project, which is an EU project. And that still runs for 1.5 years, so we still have some time. Any other questions?
Any other question? No? Okay, so I think let's conclude the talk. So please join me in thanking him again.